Okay, good morning. I think only Anirudhan seems to be present. Okay. So let's hope some more people join. Still a minute left. Let's start sharing the screen. Yeah. So today we will begin our discussion concerning the Poisson process. So it's one of the most important processes, and this. Okay, let me not make such a statement now. We will see later. So this process we will derive using certain very natural postulates or assumptions. So we shall denote by capital N at small t. So that is our base one, the stochastic, the process, the time variable varies over the continuum, 0 to infinity. So this is a stochastic process, of course, defined on a basic probability space, and it takes values in 0, 1, 2 non-negative integers. So the symbol capital N, which is used to denote this, it sort of indicates this is going to denote certain number. So this is something like a process which counts the number of times certain types of the events of interest occur. So that is perhaps one of the simplest kind of process one can hope to see in continuous time. It's a slight extension of, in some sense, the Markov chain which we had studied, because those things were taking values in positive integers, non-negative integers, and things like that. But here, the time is allowed to be a continuum. So that is and this time being allowed being continuum is not purely a kind of approximation. So, okay, we will see. So as this denotes a number, at time 0, the process is assumed to be 0, n0 equal to 0. And for every t greater than or equal to 2, nt is a non-negative integer valued random variable on this basic probability space omega ap. So note it down if you want. Okay. So the next postulate is, which we denote by n2, is if s is less than t, the time s or the time point yet s is less than t, then n of s is less than or equal to nt. In other words, this stochastic process is a non-decreasing process. That is, if you fix, I mean, this nt omega is a random variable. I mean, nt is a random variable, so which means this for each t, nt is a function on capital omega, taking values in integers. So if you fix an element little omega in capital omega and consider this nt omega as a function of t, so as a function of t, it is a non-decreasing function. So this is we are assuming that ns is less than or equal to nt if s is less than t. So therefore, nt minus ns, it denotes the number of events. I mean, we will be studying certain phenomenon and the events of interest means the interest in that particular context. So it's number of events in the time interval s to t. Remember that here we are making it s, open at s and closed at t. So NIS would, in particular, NT would be NT minus N0. So that is, N0 is 0. So that is the number of events in the interval 0 to t. And any process satisfying these two postulates, N1 and N2, is called a counting process. So the process we are wanting to look at now is a counting process. Please note it down. As we have seen in the previous course, one, say for example, in the case of the previous course, the stochastic process was Xn. So if you want to study, that means you are wanting to see or have some this thing about as time goes by, how the process unfolds or evolves. Which means you have to have some kind of a, perhaps a relationship which is forced by the kind of problem you are studying and so on. If you assume that all NTs are independent of each other, that is not going to be interesting. As a matter of fact, in this case, independence would not make sense because we are already assuming that if S is less than T, NS is less than or equal to NT. So if you know N of S, you already know that for any time point exceeding S, the NT will be greater than or equal to that number. So that the notion of independence, intuitively, it is sort of against assuming that this condition is against that. So you cannot do that. But we can have another assumption. This is the third postulate, an important postulate, which we denote by N of 3. The process NT, t greater than or equal to 0, that has independent increments. What does it mean? If you take, for example, T1, T2, T3, then NT1 minus N0, NT2 minus NT1, NT3 minus NT2. So you have 3 random variables. And note that NT1 will take values, any integer value, any non-negative integer. NT2 minus NT1 can also take any non-negative integer value. It can be 0 if NT2 equal to NT1, and so on. So in other words, in some sense, these kind of random variables, that is the increments, may be on some kind of an equal footing. So one assumes, the assumption here or the postulate here is that NT1, NT2 minus NT1, dot, 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 NTN minus NT at N minus 1, these are all independent random variables for any N, 2, E3, etc., etc., and for any T1, T2, Tn, which are sort of increased. So in the kind of in the this thing of nt minus ns denotes the number of events in the intervals s to t. So this means that the number of events in disjoint time intervals are independent random. So that is the reason why we here made it as the number of events of interest in the open interval st, open at s and closed at t. So, for example, nt1 would be the number of events in 0 to t1. This would be in the interval t1, t2, open at t1 and closed at t2. That is up to t2. And so those intervals become disjoint time intervals. Note it down, please, if you want. This is a very important postulate. Process with independent increments, that's kind of fairly important classes of processes. In some sense, this is a kind of natural continuous analog of sum of IID random variables. Of course, sum of independent random variables. Our next assumption will make identically distributed kind of assumption. Okay, the next postulate. The process NT has stationary increments. What does it mean? If you take two time intervals of equal length, may be disjoint, may not be disjoint, but they are of equal length. So for example, the interval s to t as well as s plus h to t plus h both have the same length, namely h. So if nt, I mean in that case, if s, t and h are like this, nt minus ns and nt plus h minus ns plus h have the same probability distribution. So that is the probability law or the probability distribution of the number of events in an interval you consider at a random variable, and its probability distribution depends only on the length of the interval. So the process has stationary increments. So this assumption, as you will see, will simplify certain notations and so on. We'll also indicate how, if this assumption doesn't hold, then what happens. All right. So we have two more postulates. That is, okay, we'll go to that. So the probability of two or more events in a very short span of time is negligible. What does it mean? That is, probability of two or more events in an interval of length h is probability nh plus nh greater than or equal to 2. Probability of nh greater than or equal to 2. That is the probability of more than two or more events occurring in the interval of length h. If this h is small, this divided by h goes to 0. In other words, this probability, since by our second assumption, this is n of h will be increasing or rather non-decreasing as h increases. So as a function of h, this is a non-decreasing. And as h goes to 0, this will go to 0. But what this assumption says is that this goes to 0 at a faster rate than h itself going to 0. For example, this may be only a function of h squared. So in that case, h squared goes to 0 faster than h, or something like that. So instead of every time making this kind of instead of writing this, there is an abbreviated notation for it. One says probability n of h greater than or equal to 2 is small order h. This little o here is also pronounced small order h as h goes to 0. And when you come across this kind of a statement, it means precisely this. So this is an abbreviation for writing like this. So in other words, this prevents the possibility of bulk arrival of events. That is the situation of what one may consider slightly rare events, you can say. Okay. So this is the fifth postulate. Okay. Note it down if you want to. Then the last postulate. There exists a constant lambda greater than 0 such that probability n of h equal to 1. That is, this is the probability of exactly one event in an interval of length h. So that is roughly proportional to the length of the interval, and proportionality constant is this lambda. So one writes this as, this may not exactly be equal to lambda times h, but then lambda times h plus something which is going to have the property that this guy divided by h goes to 0. Yeah. So in other words, the probability nh equal to 1 is lambda times h plus theta h, where limit h going to 0 of theta h divided by h is 0. So in a short or very short time interval, probability of exactly one event is roughly proportional to the length of the interval. Note it down. So this here we are able to take this lambda to be a constant is a kind of result of the stationary increment property. If this property doesn't hold, there we'll have to take to be lambda to be a function of time point as well. So note it down. So if you have any question or any comment concerning any of these postulates, you may feel free to ask now. Okay. So before we proceed further, let us just look at this small OH notation. So we say if fh is small order h, f is a function, small order h, if as h goes to 0, if this happens. By the way, have you come across this notation in any other course?
Algorithms course in the third semester. Yes.
Algorithms.
Yeah.
Did you also come across big OH instead
Yes.
of? Huh?
Yes.
Okay, okay. So that means it is bounded by that k times that whatever occurs within the parenthesis here. Yeah. So this is stronger than that assumption, in the sense that it gives you more information. Yeah, algorithms course, yeah, the numerical analysis you will have come across. Statistics course you might have come across. Anyway. Okay. And the advantage of this notation is if you have two functions f and g, both are small o of h, then their sum is also of that. Sum also means the difference, because if g is small o h minus gh also small o h. And similarly, if fh is small o h as s goes to 0, and alpha is a bounded function, in particular, for example, alpha is a constant, and so on, then alpha times h multiplied with fh is also small h. So in particular, with these two together tells you that if f and g are small order h, any linear combination of f plus f and g is also small order h. Yeah, I suppose in your approximation or algorithms course, you would have seen several examples. In terms of polynomials of h or logarithm of h, e to the power h, e to the power minus h, and so on. Okay. So now we will see what all these postulates lead to. Okay. So now define P sub n at t is probability capital NT equal to little n for n equal to 0, 1, etc. and t positive, t rather non-negative. So P at 0, say what we are up to is, today we will look at n equal to 0. So P0t we are going to consider. So we are going to derive an ordinary differential equation for P0, P sub 0. Okay. P sub 0 at t plus h. So by this definition, it is probability that n at t plus h is equal to 0. So this is the number of events in the interval 0 to t plus h. So the interval 0 to t plus h is union of 0 to t and t to t plus h. So if the number of events in the interval 0 to t plus h is 0, which means in each of the subintervals 0 to t as well as t to t plus h also it should be 0. That's what this means. This is by our postulates n1 and n2. So that is, we are just using in this derivation that n capital N is a counting process. Now use the property of this important property, independent increment property. So this event is the intersection of the event nt equal to 0 and nt plus h minus nt also equal to 0. So they are independent events. So the probability of that intersection is the product of the individual probabilities. So it is, this is equal to P nt equal to 0 multiplied with P nt plus h minus nt equal to 0. So here to here, so this random variable nt plus h minus nt has the same probability law as the random variable nh minus n0, but n0 is 0. So it has the same distribution as n at h. So this probability by our fourth postulate is same thing as P of nh equal to 0. So we know that the random variable nh takes values in 0, 1, 2, etc., dot, dot, dot. And since it takes value on the non-negative integers, probability of it taking any non-negative value is 1. But from that, you have to subtract out probability of nh equal to 1 to get the probability of this event, nh equal to 1 and nh greater than or equal to 2. Now we know by N5, this probability is small order h. And by N6, we know this probability is lambda h plus small order h. So the one small order coming from here and one small order h coming from here together is also small order h. So here we have used this thing of notion of the events being rare, that is, and so on, N5 and N6. So now if you expand this out, P0T times minus lambda times P0T multiplied with H and P0T multiplied with small order H. So now note that P0T is bounded by 1. So this guy will also be small order h. So now next slide, we will take this P0T to the other side. Okay, note it down if you want. So from that, we get P0 at T plus H minus P0T is the other guy, other thing. Of course, you may wonder why we have written here this thing and also, yeah, that is no problem. Yeah. And divide the whole thing by H. So then you get that this ratio is minus lambda times P0T and P0T multiplied with OH divided by H. So the next step is we let H go to 0. So the left side you will have the derivative of P0 at T. I mean, one might, yeah, finer point is that this will only show that as H goes to 0 from the right, you get the derivative. So those kind of mathematical details I will skip. You can also prove that if you go from the left also it. So this P0T as a function of T is a differentiable function. So because of probability is always dominated by 1, letting H go to 0 or descend to 0 in the above, we get P0 prime at T is lambda times P0T for any T positive. So this is a very simple ordinary differential equation. One really doesn't need to know any differential equations basically to solve this equation. That is advantage. So from this, you bring this guy here, and then you see that it is the derivative d by dt of log of P0T is a constant minus lambda for t greater than 0. So a simple indefinite integration here gives you log P0T is minus lambda t times Of course, don't forget the constant of integration plus C. Consequently, P0t is the e to the power of this exponential of this. So that gives you this, and e to the power little c, you treat it as a big constant, capital C. So P0t is capital C times e to the power minus lambda t, t greater than or equal to 0. So to evaluate that capital C, we use the initial value, and the initial value comes from the first postulate. So P0 at 0, that is probability N0 equal to 0 is 1. We are assuming that N0 is identically equal to 0 in N1. So that gives us P0t equal to e to the power minus lambda t for all t greater than or equal to 0. So we will stop here for the day because I want to do the derivation of P and T at one go for any n greater than or equal to 1. So if you want me to go back to any of the slides today, please tell me, or if you have any questions or comments. Okay, so I will stop sharing now.
Thank you, sir.
Yeah, so again, the attendance is rather disappointing, but I think now I am just taking it as a fact of life. Okay, so those who want to gain some pieces of entertainment by attending the class, they can do so. So this will be put up soon. And if you don't have any queries, I shall end the session now.
Thank you, sir.
Thank you very much and take care. We will meet on Friday.
Thank you. Bye.